Hola, chaps. Mr. Turek here. This is for stoichiometry, volume calculations for chemistry. On CK12, they had an instructional video that was a little bit flawed. So if you watch the video, you'd see that the guy wrote carbon monoxide when he was supposed to have written carbon dioxide, and he eventually figured that out. He also did a complicated process of calculating the volumes of the gases. He made it more involved than necessary since particular units tend to cancel out. He also didn't actually answer the second problem. The second problem asked him to calculate how many moles of reactant you need, and instead he calculated how many moles of product he needed and expressed that in volumes. All right, so a couple things I wanted to emphasize to you because I don't know if they made it very clear to you. So STP is standard temperature and pressure, where the temperature is 0 degrees Celsius, the freezing point of water. So if you're in an ice cold room at sea level on Earth, you would be at standard temperature and pressure. And under these conditions, 1 mole of any gas, any ideal gas, would have a volume of 22.4 liters. Now, it's not fun for people to drop their thermostats down to freezing. And so there's another standard called the standard ambient temperature and pressure. And this one has the same pressure as STP, 1 atmosphere of pressure, sea level, which is also 14.5 pounds per square inch, 100 kilopascals, that's a metric unit of force, or 750 millimeters of mercury. That's the height of a column of mercury where the pressure of the atmosphere is enough to push the mercury that high up in its container. But the difference is that the temperature is now raised up to a more comfortable 77 degrees Fahrenheit, which is 25 degrees Celsius, which is 298.15 Kelvin. So standard ambient temperature and pressure. Under these conditions, because the temperature is higher, the volume for 1 mole of an ideal gas is also a little bit higher. It's 24.79 liters per mole. This isn't one I hadn't encountered before CK12, but it's out there and they might zing you with some questions referring to standard ambient temperature and pressure. Realize that the volume is 24.79 liters per mole, whereas it's STP, the more common for physics problems and chemistry problems, is 22.4 liters per mole. All right, so having had told you that, I believe just before the school shut down, I passed out this homework problem. And actually, even before I get to this one, let's just practice with stuff from your house. So I have here a bottle of distilled white vinegar, and it says on the side of the bottle, which I suppose I could turn here and have you see it this way. It says this one has a volume of 32 fluid ounces, which is 1 quart, which is 946 milliliters of volume. So if this were 946 milliliters of volume, and I were to empty out all the liquid inside of it and just fill it with air, a mixture of gases, nitrogen and oxygen. My question for you is how many moles of air can this container hold? Of course, at standard temperature and pressure. So not standard ambient, but standard temperature and pressure at STP. So calculate, please, how many moles of gas fit into 946 milliliters. We don't really need to use the fluid ounces. We don't need to use the quarts. We can get away with just doing this in metric units because after all, 22.4 liters is a metric unit. So first thing I suggest you would do is convert 946 milliliters into liters. No doubt you're eager to be tested on this, and you know that 1 liter is 1,000 milliliters. And what I have to do is choose my units in this conversion table so that they cancel out. And that means divide by 1,000, which means move the decimal point 3 places to the left. And now I have 0.946 liters of volume in this container. Next step is I want to convert that to moles. I know that 1 mole of any ideal gas, and all gases behave as ideal gases for practical purposes in our chemistry course for now. 1 mole of ideal gas occupies 22.4 liters. So it's that simple. It's a ratio that says 0.946 out of 22.4 means I get 0.0422 moles of gas would fit into this vinegar bottle if it were empty. Not much. A mole is much larger than this in volume. All right, well, I do have a slightly larger container. Here's an orange juice container from Trader Joe's, and it says its volume is 1.53 liters. Not that you can see that so well, right? So let me make it easier for you to see, perhaps. You can kind of see that. Ways of making it darker or brighter. That makes it worse. This makes it better. Well, eventually I think you can figure out it reads 1.53 liters. All right, so now the question becomes, how many moles is that? If I were to take this empty container and fill it with air, which is what it has in it right now, how many moles of air does it contain? And the answer is 1.5 liters, which I need to change. You can see what I'm doing. Oh, this is going to cause an adjustment here. There we go. And an adjustment there. And finally, you can see what I just wrote. 1.5 liters times 1 mole for every 22.4 liters. Calculator. Doop, 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 deep, deep, deep. That didn't go so well. Doop, 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 beep, beep, beep. There we go. No doubt you've done this already. You beat me. All right. So now I get 0.0 to 3 sig figs. This would be 670 moles. This number to 3 sig figs, 6, and then this rounds up to 70. All right. So that is this empty orange juice container. Stay healthy. I also have an empty vinegar bottle, more substantial. This one, whoa, if you could read it. Oh man, what does it say if I were to focus that? It would say, wait for it, wait for it, wait for it, assuming it's doing it. Aha, 3.784 liters. All right, so let's work with that number. 3.784 liters of this volume corresponds to how many moles? Calculate, please. Very simple conversion, as you can see. 1 mole of any gas is equal to 22.4 liters at standard temperature and pressure. Well, bring it back to where you can see what's going on. So, see if we get it correct this time. Doot, 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 beep, beep, beep. That sounds more correct. What'd you get? I got 0.169 moles. So even this is 17% the volume of 1 mole of a gas. So if I flip that thing around, how many 1 gallon containers would I need to contain 1 mole of gas? The answer is I would need almost 6 gallons of empty containers filled with air would contain about 1 mole of gas. So the last thing I would share with you, haha, kitchen bags. Okay, well, these are 13-gallon sized kitchen bags. And the question is, how many moles of gas would fit into a volume of 13 gallons? And of course, they don't have, oh, they do. So I'll read to you the value that was on the display. Here, let me show it to you. Oh, let's see. If you zoom in just right, you'll see that 13 gallons corresponds to 49.2 liters. 49.2 liters. So 49.2 liters, convert that. Each mole requires 22.4 liters of volume. And now you should have your sound effects mastered. And I get 2.20 moles to 3 sig figs, 2.20 moles in the volume of a kitchen trash bag. All right, so once upon a time, I assigned this worksheet to you called Mixed Mole Problems, and I told you to skip the problems that we didn't know how to do. So I told you to skip problem 2. Why did I do that? Because you hadn't learned about volume stoichiometry yet. Well, let's see how this goes. The first problem was, how many grams are there in 1.5 times 10 to the 25th power molecules? Well, the answer is 1.5 times 10 to the 25th power divided by Avogadro's number. Now, did I store Avogadro's number in here? I think I deleted it. Nope, it's in here. So I could go 1.5 times 10 to the 25 divided by Avogadro's number, and I get 24.9 moles, which doesn't even answer the question, 24.9 moles. However, I need that piece of information to do number 2. Number 1 was how many grams, and you look up on the periodic table the mass of carbon, which is, let's just call it 12, the mass of oxygen, which is 16, and there's two of those, and so 16, 12, 17, so it's 44 grams per mole, and I have 24.9 moles, so I can calculate 24.9, let's just do it, times 44, and so I get more than a kilogram, 1.095 kilograms of carbon dioxide. All right. Now, the volume is a problem you can now do. Instead of skipping it, problem 2 was, what volume would this carbon dioxide occupy at standard temperature and pressure? Well, ta-da, now we can do that. 24.9 moles, and the mass of it doesn't matter. It's each mole occupies a volume of 22.4 liters at standard temperature and pressure. So 24.9 times 22.4, and I get 558 liters. You should now be able to do problem 3 as well. Problem 3. A sample of ammonia gas occupies 75.0 liters at standard temperature and pressure. How many molecules is this? Well, work it out yourself. Pause this videotape and then I'll try to catch up to you. Okay? First, 75 liters needs to be converted into moles. I know that 1 mole is equivalent to 22.4 liters of volume. So, step 1, 75 divided by 22.4. Enter. So I'm working with 3.35 moles of ammonia gas. Each mole is Avogadro's number of molecules. So when I multiply this by Avogadro's number per mole, I will have the answer. So this times, and I've stored it in my calculator as alpha n, I have an answer of 2.02 times 10 to the 24th power molecules. Hopefully you can see that all right. All right. Now you should be able to do number 4 yourself. If I have 3.35 moles, and each mole is the mass of nitrogen, which is 14, plus 3 hydrogens, we'll just call them 1. So 3.35 moles times 17 means I have approximately 57 grams of ammonia gas is my answer to number 4. And then how many atoms are there in this many molecules? Well, each molecule has 1 nitrogen and 2 oxygens. So there are 3 atoms in each molecule. And if I have 1.3 times 10 to the 22 molecules, then I have 3 times that number of atoms in that sample. So 1.3 times 3 times 10 to the 22nd power. Let's just do it. 1.3 times 3 is 3.9, and the exponent's not going to change, times 10 to the 22nd power atoms. Okay, you should now be able to do problem 6. A 5-gram sample of oxygen gas is in a container at standard temperature and pressure. What volume is the container? All right, pause, calculate it. Now play and see if you match me. So 5 grams of O2. So 5 grams times the number of moles divided by the number of grams in a mole of oxygen. So oxygen, I'm just going to call it 16. So 2 oxygens is 32. So for every 32 grams I have of oxygen, I have 1 mole of oxygen. So 5 divided by 32, Julia would say, doop, 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 beep, beep, beep. I get 0.156 moles. I'm at standard temperature and pressure. So now I use the conversion that a ideal gas has a volume of 22.4 liters for each mole at standard temperature and pressure. So this times 22.4, and I end up with a nice round number, 3.5 liters. Number 7, how many molecules of oxygen gas are in the container in problem 6? How many molecules? Well, 0.156 moles, 0.156 moles times Avogadro's number, which I'm representing as n subscript naught, they would say, per mole will tell me how many molecules I have. So 0.156 times Avogadro's number, and I get 9.34 times 10 to the 22nd power. That would be the number of molecules. 9.39 times 10 to the 22nd power molecules. Put some units down on your answers. Now, each molecule of oxygen, being diatomic, has 2 oxygen atoms. So I need to double this number, which is 1.88 times 10 to the 23rd power atoms. And there, I've just done your entire worksheet for you. Makes it hard for me to give you points for doing it now that I'm sharing with you the secret of how to do all these problems. A long time ago, you had a balanced chemical reactions 2 handout worksheet. I thought, why don't we just make a couple quick comments about this? Because on the CK12 video, the guy made it more complicated than necessary. Here is a balanced chemical reaction for potassium chloride, perhaps? Let me look that one up. ClO is hypochlorite. ClO is hypochlorite. Potassium hypochlorite and potassium chloride yielding oxygen. It says here, for every 2 moles of this, I need 2 moles of that, and I end up making 1 mole of this. So my claim is, if I gave you 2 moles of this, and if this were generated at standard temperature and pressure, this oxygen gas, how much volume would it have? The answer is 22.4 liters, because each mole of any gas at standard temperature and pressure has a volume of 22.4 liters. Half a trash bag. Same thing with this reaction here. So if I gave you 1 mole of hydrogen peroxide and excess water, what volume of oxygen would I have as a product at standard temperature and pressure? And the answer is, well, I only have 1 of the 2, so I'm only going to use 1 of the 2 that I need here, and will produce 1 of the 2 that I want to produce, and I only will produce 1/2 of the oxygen here. So the volume of oxygen would be half of 22.4 liters, which is 11.2 liters. Here's a combustion reaction. You love combustion reactions, particularly balancing them. So this is C4H8, and I don't recall if that's butane or what that one is. But as a balanced chemical reaction, I need 6 moles of oxygen for every mole of this fuel to produce 4 moles of carbon dioxide and 4 moles of presumably liquid water. So if I had 22.4 liters of oxygen, by this ratio, I would only have 2/3 of 22.4 liters of carbon dioxide gas generated. Yes, I like those sound effects that I'm creating in the background. So I think that's enough for you to figure out this particular CK12 assignment. This was for stoichiometry, volume-volume relationships that was assigned over the weekend. All right. Ciao.